recording now, and I want to. I think from all the talks today is quite interesting. I think I want to just make a few brief remarks, and that's sort of the hope is that I'm going to trigger some discussion. So in my point of view, I think there are three things that are right now on the table related to the phenomenology part of the vorticity and polarization. The first thing is that our large angular momentum J induce fluid vorticity structure. I think this is a pretty robust thing. And I think all different kind of models, including hydro model, transport model, I think everybody had pretty much consistent message. No matter which vorticity we're talking about, I think different calculations seem to show quite consistent patterns of magnitude, distribution, and so on, and their dependence on beam energy and all that. I think here, so this is pretty robust, I would say robust. What I think is important to understand further, I think, is that something that Yuri mentioned, namely the initial condition. I think this is really actually quite important. When that angular momentum is deposited into the system, so you really have to develop some initial vorticity to carry that global angular momentum. I think this is one thing that have not been fully understood, I would say. Namely, how each model exactly set up the initial condition, especially in terms of longitudinal initial condition. Now, how those are going to, be consistent with the directed flow, which actually has a quite non-trivial dependence on beam energy. And I think that's important to understand because this pattern that I'm drawing here is directly related to direct flow as well. Okay, so I think this is one thing I think I would think that would need more understanding. And that had also a connection to other interest at, for example, beam energy scan. For example, when people want to develop bulk evolution model for low energy and for baryon distribution and so on, and then those are also related to the initial condition, especially in the longitudinal direction. My second point is that I think the mapping from omega, this whatever vorticity, to the global polarization, let's say lambda bar, this seems to be also very robust, I would say. I think almost all models can get that right. Well, depending on how you tune your parameter, but I think that's okay. I mean, within reasonable parameter range, all different models are giving very reasonable description of the global polarization measurement. So that's good news. I think this kind of robust established phenomenon. And in this step, it seems that all the details don't matter too much. For example, are there going to be viscous correction, or is there going to be off equilibrium correction? Those seem to be not very much relevant because it looks like we can already describe data pretty well. However,
can I ask questions?
Yes.
Just related to this one, you said robust, we have to check it. The reason is during discussion, where the global polarization calculated in the hydro model depending, so that if the lambda polarization does not change from TC to TK, then that's fine. Because then it depends on where you stop your you stop your freeze out, right? So
that's correct.
Nobody has checked. Maybe that's true. Nobody has checked. Maybe indeed, if, for example, if Jun Wang used MPT again, he can calculate the lambda polarization at any time from TC to TK. Maybe it's a constant for some reason, right?
In the AMPT, actually, I think that there is already such information because every particle is formed at a given time. So you have a whole.
Did they start the time evolution? Really, the lambda polarization does not change from TC to TK based on AMPT, because you can calculate the vorticity at any time from TC to TK. Then you can just thermal vorticity to calculate lambda polarization. Let's check.
But that's a continuous process. Actually, in the AMPT, you don't really have the concept of TK and TC because each particle just frees out.
That's not what I'm saying. What I understand from John Watt's calculation is he run MPD to total kinetic freeze out. Then he does the coarse graining. Then you the thermal vorticity lambda polarization. He found it agreed with experimental data. Of course, he said I can stop the MPD earlier. Then I use the same freeze out velocity distributions of vorticity and use the thermal vorticity to calculate lambda position.
Oh no, that's not going to work.
No, you can do it. You can do it.
Listen, we did the MPT, of course, many times. Here's what I'm telling you. So it's a continuous process in the MPT, and at any time, okay, so we do like 1 million MPT event, we average them on the call screen. At any time moment, you have a vorticity profile, and you can convert that vorticity profile at any time moment.
Lambda polarization.
Can I comment on
this?
Yeah,
you can convert that to
you calculate vorticity.
Polarization.
Does,
no, but the thing
does
is
it
that
change? How does lambda polarization change with time?
Let me finish.
Yes, can I comment on this?
Please. Not all the lambda anti-lambda are produced at a single time. It's a continuous. We actually look at, even the lambda, production time histogram. It goes like this. It's not that you produce all the lambda at one single time moment. It's a continuous process.
No, that's not my questions. My question is
but no, I understand your question. Let me finish. You're saying, okay, I take my evolution and I stop at 5 firm and see what happened. What I'm telling you is that result cannot be compared with the experiment because not all the lambda are produced yet. That's what I'm saying.
I agree. But the point is, in hydro calculation, they do not use the TK. They use, some people use TC, some who are half between TK and TC. They all agree.
I think, okay.
Then the question, why?
Your point is well taken.
Question. I can always calculate. I can always calculate lambda polarization at any time during hadron evolutions. But at any time, I know the vorticity distributions. I know I can use thermal to calculate.
Yes. In the AMPT, we can do this, and we check this. The polarization for lambda would decay with time.
Okay. Did you get a constant lambda polarization from TC to TK?
No.
Which way go? It decreases or increases? Decreases,
decreasing.
Right? That's right, decreasing. Therefore, in the hydro approach, you have to be careful where you stop your hydro. Then you get different lambda polarization.
Chemin, look, your point is well taken, first of all. And second, I think for many of the hydro calculations, they take into account that whatever you compute from your Cooper-Frye need to be reduced by certain fraction due to resonance and all that. I think
I see.
That at least that's my understanding.
Yeah, I agree.
And but I think your point is well taken.
They should just couple to afterburn. If they couple to URQMD, then redo it. Then there's no ambiguity. Right. Okay. Sorry.
Yeah, I agree. Yeah. No, that's a good point. Yeah. So you're saying some further checking is needed. That I agree. But I think overall, I would consider this still to be quite robust. But I think there are, of course, certain issues that are the important issues here, namely, there's the splitting. Now, this splitting, I would say, we need certainly more experimental work. I mean, that's unfortunately not completely done yet. Namely, we want to confirm that, with a smaller error bar, there's a robust splitting between lambda and anti-lambda. On the other hand, I think we already heard a lot of different theoretical proposals, which is good. So I think this is one thing that needs to be resolved. And the other thing, in my view, I think all the vector method, that make me very sort of troubled because I really sort of don't quite understand why, how to reconcile this vector meson measurement from inner star or ALICE with our lambda. I mean, it's not easy. I think this is going to perhaps, be an important question that need to be addressed. So I'm just going to take another minute just to say that then there's all the question about local polarization. I think so far, I would say this is really sort of very fragile kind of measurement. It's very small and it does have a variation or modulation, which we cannot explain or we haven't converged yet. There are many proposed different, vorticity, or I think, for example, viscous correction, namely this kind of mapping from omega to P is perhaps not good enough for local polarization, or which omega you should use. All these questions. I think this is both good and challenging. I don't see a clear solution at the moment, but I think this is good because then we have something that we can sort of some puzzle we want to solve. So I will stop here. This is just really to start discussion. So guys, please go ahead.
Yeah, I want to comment about this vector meson. Actually, vector meson, the phi meson, it seemed the phi meson spin alignment seemed to be it seemed that we can understand it as the phi meson classical field, the phi meson field. Actually, you know, the vector meson field or mean field or whatever you call it can polarize the S quark in the same way as the electromagnetic field. So I think it seems that the vector meson, the phi meson spin alignment can be understood by using this vector meson field or phi meson field. But the K star, the situation of the K star is more complicated because because of its shorter, very short lifetime. So it is not as clean as phi meson, which has a long lifetime. Okay, so maybe I will talk a little bit about this topic on Friday. Thank you.
So you're pointing to the general sort of meson mean field effect, especially that perhaps are relevant at no energy, right?
Yes, exactly.
But
can you say more about what is the phi meson mean field?
What?
Is there the phi meson mean field there?
Yeah. Phi
in the
meson mean
hadronic
field.
matter?
No,
the hadronic matter?
Whatever you call it, it's like a field. I mean, vector meson or phi meson field. Coupling to the S quark. Coupling to the S quark.
Here, the question I see that for what you said, and also for I think Yilong talked about the meson mean field.
Yeah, same thing.
Yeah,
it's the same thing.
The important thing is that I think we need some other constraint on those kind of fields. For example, dynamics from, I don't know, nuclear physics, you know, hadronic physics, that can help constraint, because otherwise, you know, of course, one could imagine that one could always build some mean field potential to explain experiment, but we need some independent constraint on those mean field models.
For the S quark, I mean, there's almost no experimental data for the S quark. You know, the PDF, parton distribution function for S and S bar.
For example, would that kind of mean field affect the you know, yield or spectral or, you know, flow of strange particles? That could be also checked.
I don't know any data can constrain this part, but there's only one hint from PDF, parton distribution function for S quark and S bar. In the longitudinal direction, S and S bar is not equal. Therefore, there is a net strangeness current, which produced this phi meson field. So this is the only hint from experimental data of the.
But one would naively think that this would affect something like a K meson, because we know that, of course, for K meson, for example, the direct flow in no energy is quite strange, right?
Yeah, the K meson is not as clean as the phi meson because the K star. Oh no, you mean the K meson or what?
Yeah, K on the mean field is well known. K bar is well known in the low energy Beverlek GSI physics, because K on is repulsive potential, weak repulsive potential. K minus is very strong attractive potential. Say attractive potentials, not very strong. It's attractive potential.
But
right, and they measure the V1, right? They found the V1 of K-on.
So this scalar meson plays no role because it cannot polarize.
Sure, I mean, you have the vector meson. Yeah.
You have to use the vector meson field. Yes.
Yeah.
Okay.
But if you if you look at the NGL model, then you can introduce a vector coupling if you want to. Then both S quark will see repulsive couple. If you generate NGL to SU3, then S-quark will also see the positive potential, S-bar will see the weak attractive potentials.
From NGM model also, you can also.
Sorry, that I think there are also other people who want to say something, perhaps. So
Sure.
Yuri, you want to say something?
I
saw you.
Yeah, I think the discussion kind of drifted away quite a bit from the moment I raised the hand. I caught. I mean, I was listening to that on the background, so I caught that there was this discussion about the robustness signal of the lambda polarization, I guess, and this discussion that what happens if you shift the production points, right? If you shift the production temperature or stuff like that, or you shift the time, the moment in time when the lambdas are produced. So I think it's. I mean, I looked at that a little bit. So when I was showing this robustness signal, I mean, when I was showing the slide with the so-called robustness of the signal, among other things, I was also variating the energy density when you compute the polarization of lambdas, which correspond to different temperature, basically. So I was shifting. I was changing the energy density by plus minus 40%. So that's like, I don't know.
If
maybe,
you want to show your slide, that you can.
Yeah, I can do that. Let me see. Wait. Okay. So that's that slide. Yeah. On the so that's the plot on the left. So you see that there is this last item in the legend. The epsilon switch plus minus 40%. So that's the variation of the polarization when you change the energy density of the particularization. So the energy density where lambdas are produced. So you see that compared to basic scenario, this shift is kind of very small. So it doesn't really alter anything much. And there was also a question about the hadronic, about the resonance contributions and the afterburner. I mean, the resonance contributions, that's what we have shown. I mean, it will be discussed, right? But what we have shown is that the resonance contributions are generally like overall small effect, surprisingly. I think it's somewhere, wait, I think it was, okay, no, I think it was actually at the very end. Yeah, here. I mean, you can basically see the difference between primary lambda and feed down corrected lambdas on the top plot. So that's not much. And the afterburner is actually a problem because, I mean, UrQMD, I mean, there was a statement that why cannot one run UrQMD, right? I mean, UrQMD doesn't have spin degrees of freedom. Neither does any cascade on the market. I mean, you cannot basically, you will lose polarization if you feed it into UrQMD. I mean, it doesn't have spin degrees of freedom simply. So the afterburner is actually, the question of afterburner is actually something which hasn't been addressed yet. And I think it's like something to do actually. Yeah, so that's my 5 cents into the discussion. Sorry.
That's very helpful. Actually, that answered some of Trement's question as well. And I think you're right, because in principle nowadays, I mean, running hydro plus cascade is not a big deal. But the problem is that you said that in the UrQMD, you don't have the spin information for those hadronic scattering. On the other hand, so here's what I think. If all the particles are polarized as they should, okay, of course, we only measure lambda because we are able to measure lambda. We cannot measure proton, but suppose the protons are also polarized. Any particle spin should be polarized. If that is indeed the case, then I would imagine that scattering among those polarized particles are not going to change the overall polarization for each species too much. So that would be saying that maybe the hadron cascade would just be a minor correction to the observed or calculated polarization. And your resonant decay seems to be like at the 15-20% level, which also I think is very reasonable.
Yeah. Okay.
Okay, I think there are further comments. I think Oleg, you want to make your comment?
Thanks. I was going to add something to the problem of vector mesons. And as I already said, just in the discussion of the last talk, the vector mesons should be accounted for if the axial charge is calculated. And what came to my mind that maybe the phi field can be some complementary way to take this into account. So this would mean that maybe, and also what John said about that the strangeness is related to the maybe somehow estimated from what we know from just pattern distributions. And what happens that moment of strangeness contribution to axial charge, which is of order of some percent, can be estimated from the axial anomaly. We did it a while ago. So this means that maybe axial meson contribution to axial charge, well, strangeness in pattern distributions and some field, some mesonic field, maybe somehow they can be not completely unrelated. And as to the problem, discussed problem of some interplay between chemical and kinetic freeze out, well, it's I am not an expert at all, but somehow in the problem of the hadronic polarization, with which I'm more familiar, there is a so-called final state interaction. So when produced particle interact and they can change also polarization. Maybe in this transition from chemical to kinetic, it can be some analog of final state interaction. This what is came to my mind. Thanks.
Yeah. I think I guess one of the question that say suppose let's say suppose we start some hadronic phase with all the particles that are already thermally polarized, and then they interact with each other. The final state interaction.
Right, exactly. This is
is that going to redistribute the polarization or not? I guess that's the question.
Well, one possibility is that it can be redistributed, but another point is polarization may also emerge in the rescattering. So if particle rescatter, it can change polarization. This is a point. And if really in the transition from chemical to kinetic, I think it may be considered rather as a sort of rescattering. Maybe the polarization can change. But if, of course, there is a vorticity, but I don't know whether it's not only vorticity is required, but also thermal equilibrium. After the chemical result, is the equilibrium after that?
Right. But perhaps not the global polarization, right? So we're looking at all the spin projected to the y direction, let's say, global y direction.
Well,
so if yeah.
I mean that if particles are scattered, that the polarization which is normal to the, of course, scattering plane. But if they are going, if they are flying predominantly in the reaction plane, well, in this case, for final state interaction, rescattering would contribute to global polarization. This is what it seems. But in general, the interplay between I would say hadronic polarization normal to the scattering play and heavy ion global polarization, I think it's quite interesting problem. So one one is expecting it was I believe the original suggestions of Jacob Rafalski that polarization normal to scattering plane should be diluted. And instead of this, it's just suggestion of Liang and others, there is a global polarization. But how this transition happens, whether it was studied experimentally, I really don't know. But maybe just for scattering, they somehow may coincide. So there's because for scattering, I mean the scattering plane somehow is defined by the reaction plane. Maybe.
Yeah, generally, I think yes. That I think I will agree that there are many questions related to the hadronic phase that we haven't paid enough attention to. I think that's something need to be sorted out, especially because the polarization effect seems to be the strongest at lower energy, or the hadrons are supposed to play more role. Yeah. So Francisco, you have a comment here, I guess.
Oh yeah. Can you hear me?
Yeah.
Okay, so I think the point that you raised in in your slide, the first point you raised is very well taken, and I've always wondered what would happen if the initial hydrodynamic conditions were changed to the polarization. So an answer has been given by Yuri in his talk, where he showed that by changing the parameters of the initial conditions, then you get quite robust prediction for the global polarization. But we don't know what would happen if we for the local polarization. And in view of the sign problem, I think this is very interesting. And I would encourage everyone who is dealing with hydrodynamic code to test this. And then I have a question to Yuri. So what room do we have for the initial conditions now? So for instance, in his code, if we can we introduce, say, some initial longitudinal flow gradient or something like this, you know, without, say, spoiling the agreement with the momentum spectrum observables or the elliptic flow?
Well, I think that you mean some sort of initial shear longitudinal flow.
Yeah, I mean what I mean is that can we change, say, the initial flow profile, for instance? I know that maybe this is constrained in your code, but to what extent is it constrained? So can we change somehow? I don't know how, but somehow the initial velocity profile, both longitudinal and transverse, and see what the repercussions would be on the final local polarization.
Well, that's actually a good question. I mean, the initial longitudinal profile can be quite constrained by the directed flow, and in principle for the initial transverse flow, in principle there are constraints from PT spectrum and from elliptic flow. So this you don't want to lose, of course. So there isn't that much freedom, I think, but in principle, what one can do, I mean, it's not a simple test, but in principle, what one can do is one can kind of try different shapes of the initial state, like different shapes of the initial energy density profiles, probably, with different initial transverse flows, so that each of them would reproduce more or less the PT spectra and V2. And then look how local polarization differs in those calculations. But it's not entirely easy test, but it can be done in principle. I mean, basically testing different initial states in a sense.
Sorry, actually, all this is defined by initial cascade model. So URPMD, for example, or other kinetic model. So this is the freedom only to choose the time when we turn from kinetics to hydrodynamics. So not much freedom.
Yeah, can I make a comment to Francesco's questions? Since your problem get the local polarization incorrect, the sign right, because you count that time derivative of temperature, that's always negative. So I don't know how can you, no matter how you change the initial condition, that is just fact. Temperature must decrease with time. But so you can never change that sign.
Sorry, that
Am
formula,
I right?
That formula was taking some assumptions. I mean, this was a say quite a nice formula to see, but
Yeah.
I mean, it's not really hydrodynamic model formula. I mean, it was derived after many, well, I mean, several simplifications. So you shouldn't take this as a realistic formula.
But suppose you're doing hydro with different initial conditions. At the end, when you do
No,
the
but I mean,
using
you mean the
thermal
formula
vorticity, you still use the same formula, right?
No, I mean,
Unless you give up the thermal
No.
vorticity using the T versus vorticity, then
No,
you solve
no.
the problem.
Can I answer?
Yeah,
The
please.
The formula you're referring to is probably the one shown by Yuri, F2 proportional to V2 through this dt over d tau. Okay, is that the formula you're referring to?
That's correct. Yeah.
Yeah. Okay. So that formula is not realistic.
I
So
see.
this was
Okay, thank you.
obtained under several simplifications, simplifying assumptions. So the formula that have been used to calculate the polarization was the full formula where say the thermal vorticity field has been calculated with the hydrodynamic simulations. So and there is this disagreement that was already observed, but they were also observed by the calculations with AMPT. So I was wondering, and the question the point raised by Jinfeng is, I think, is a good point, whether this disagreement, this discrepancy, is owing to some, not fully correct initial conditions, whether they are transport or whether they are hydrodynamic, put by hand, I don't know, but maybe the initial conditions are not completely correct. And since the polarization is sensitive to the gradients of the fields rather than of the thermodynamic fields, rather than the field themselves, so it is very sensitive to the shape of the field. Maybe there is room to, I don't know, this is to be studied. Maybe there is room to accommodate initial conditions in a way that the polarization is reproduced, the local polarization.
Yes, suppose in your calculation, you assume T is constant. What happened? You get the sign right? You can do your calculation. Just when you use thermal vorticity, you have that the beta of T or something. You just set T as constant.
No, I don't think so.
You cannot.
No, sign right.
No, you cannot.
Even you remove the part of the temperature gradient, you cannot get the correct.
It's just not using kinetic vorticity.
Oh, I see. That I missed it. Okay. Okay.
Yeah, because
So
I remember this by
that simple formula. Okay.
Jun showed that even if you use kinematic vorticity, you don't get
you don't get it right.
Yeah.
You have the T vorticity, right?
Yeah, T vorticity. It's
the point is then maybe I come to some other point, but I think the time is up already. So T vorticity, okay, reproduces the data, but we don't understand. At least I don't understand why. Because
that's true.
Thermal vorticity, as has been pointed out today, such that a global equilibrium becomes a killing vector. Therefore, it has, it appears in the formulae not by chance. It appears because it is minimal deviation from global equilibrium. And and then I don't understand why T vorticity works.
Francesco, can I make a quick comment?
Yeah, sure. I mean, I'm not the chairman.
We have checked the killing condition with our hydro calculation, and it doesn't hold at all. Okay, so you just calculate partial mu beta mu plus partial nu beta nu. It's not zero. Killing condition does not hold.
No, I agree. I mean, it should not hold in heavy ion collisions, because heavy ion collisions are not at equilibrium.
Right.
Okay.
That's the
so
point.
This is no mystery. The problem is, to me, why T vorticity works, apparently, according to your study, okay?
Yeah.
For the, I mean, it agrees with the data, at least, say, approximately agrees with the data. And thermal
Yeah, the
vorticity
trend,
doesn't.
get the trend correct, right? Exactly.
Okay, so just for everybody's sake, so for people who are not familiar with this, so the thermal vorticity that we're talking about is this guy, right? Partial mu with beta u nu minus partial nu with beta u mu. So beta is like 1/t. Now, what the T or temperature vorticity, that is this guy, which is basically the same, except now you use, instead of 1/t, you use T, right? So it looks like all the difference is coming from how you weigh that temperature gradient, right?
Yes.
Is that right?
Yes.
The difference from them is that here, because if you do partial mu 1/t, of course, you still get partial mu t, but t squared with the minus sign. So you are saying this is
exactly different sign. It's a different sign.
Okay, I see. So that's all the mystery here.
Yeah.
But still,
exactly.
I mean, still due to the right. If temperature constant won't solve the problem. If I say T equal to constant.
You cannot solve the problem by
okay. You check
by
it.
assuming a constant T. No, it's
Okay.
a kinetic. We also calculated the kinetic vorticity without the T. Without.
That's called kinetic.
Yeah, T is a constant just, and also you get the wrong sign.
I see. Thank you.
And the T vorticity, I mean, the T vorticity has a good feature. It reproduces the correct sign of the PZ versus the azimuthal angle. Also, it get the correct trend of PY versus azimuthal angle.
I see.
Only T vorticity. Other three vorticities cannot get these two quantities correct.
But I guess the question is that, suppose we assume thermal equilibrium, okay? So which vorticity should we use? From my understanding of this code work is that we should use thermal vorticity.
Thermal vorticity only holds when the killing condition is satisfied. But in the hydro calculation, in the AMPT calculation, in the CKE calculation, I don't think the killing condition is satisfied.
So, what in the global equilibrium,
right?
One must use thermal vorticity.
Yeah, exactly. I agree. This I agree.
Must because that is the it's the only constant quantity you can form at global equilibrium.
Yeah, exactly. This is I agree.
Because this is a consequence of a killing equation. So there's no way.
Right.
If you calculate a polarization with T vorticity, you would get something, of course, but the T vorticity would not be constant. So throughout the system, for instance, in a rigidly rotating fluid, omega beta is constant throughout the system, and omega t is not.
Okay. So this is a global equilibrium, but
a global
calculation, we don't have a global.
Exactly. We are not in heavy ion collisions. We are not global equilibrium. We only have local equilibrium.
Yeah.
So the formula with thermal vorticity took its inspiration by the principle of say minimal deviation from global equilibrium in a sense. So if the local equilibrium is not too far from global, then you expect that thermal vorticity works fine.
Right. I agree.
Okay. Yeah. But it doesn't. And so the question is whether this is a problem of initial conditions, which I think it must be tried.
Okay. Yes.
we cannot avoid this question. Maybe the initial conditions that we use in relativistic halving collisions are not perfectly fine.
Okay.
Yeah.
Or whether this is a problem of, it's a theoretical problem, and we should have used something else, some other formula.
Yeah, so let me summarize what Francisco said. Basically, he's suggesting that there are two possibilities. One is that the initial condition is not entirely correct because the local polarization is a very fragile, sensitive quantity. So a change in the initial condition could change that. And the other possibility is that the system is away from global equilibrium enough that the simple mapping with thermal vorticity may not be fully correct. So that means basically off equilibrium correction, or let's say, broadly speaking,
this is the two possibility. Yes, I agree.
Okay. I think we should allow everybody some chance to speak. So, Masoud, you want to make a comment?
Yes, I will make a comment about T vorticity, and I don't know if it is relevant to this discussion, but you can find that if you write the Lagrangian, I mean not the Lagrangian density, the Lagrangian point Lagrangian for the perfect fluid that is not charged, then you can find that the T vorticity is actually the conjugate momentum. And from the Poincare-Cartan integral invariance, you will find that the natural vorticity that comes out from that kind of formalism is actually the T vorticity, not the thermal vorticity or the kinetic vorticity. I mean, you don't even need the equilibrium in that case to define the T vorticity.
Yeah, I think this is the point. This T vorticity is conserved for ideal fluid. This is I mean, maybe provide some clue to this problem.
Yeah, you can actually write the Kelvin theorem for the T vorticity.
Yeah.
Right.
If I can, just concerning conservation of T vorticity. A few years ago with Valentin Zakharov, we developed some model of emergent polarization in superfluid pionic, in pionic superfluidity. So there are quantized vortices, and it appears that in this core of quantized velocity must be some heavy degrees of freedom. And really the quantized vortices means the constant circulation. Maybe this T vorticity can somehow be matched with this constant circulation in quantized vortices in superfluidity. I wonder, I wonder, maybe it was already done, matching of T vorticity with superfluidity.
Yeah, that's might be a possible understanding.
Okay, Georgia, you want to make a comment?
Yes, thanks. This is an interesting discussion. This is an interesting discussion. I wasn't, Masoud, thanks. I was not aware of. Just as a, perhaps this is for a different. Perhaps this isn't the right session for this. But in any case, I would be careful about this distinction versus local and global equilibrium, because in normal fluid dynamics without polarization, you can see that viscosities act like friction. So if you assume more or less local equilibrium and you put a fluid in the box and you shake it and you wait for a very long time, it will eventually reach global equilibrium. I'm not sure this is true for the sort of global equilibrium that you get with angular momentum and spin. I'm not sure. I'm not sure if this is global equilibrium is stable against small hydrodynamic perturbations. I mean, remember that vortices cause turbulence and stuff like that. To me, the argument, I mean, if anything, local equilibrium in this case is sort of the more physical one. The argument is, in what vorticity represents angular momentum, which is a conserved quantity. And close to local equilibrium, vorticity is the way angular momentum is transported. From what I understood, it was thermal vorticity, which is connected to angular momentum. No? That was sort of my comment.
Maybe Francisco can comment on that. So you're saying that there's no well-defined global equilibrium when there's angular momentum? Is that what you try to suggest?
No, I mean, there is global equilibrium. You can maximize entropy. There is global equilibrium. You can maximize entropy everywhere. You will have gradients of all quantities. I'm trying to dynamically, I'm not so sure whether global equilibrium is reached in hydrodynamics with polarization in the same way as it is in hydrodynamics without polarization. Because global equilibrium is a non-local state. I mean, you have to prepare things. You have to prepare things so that the gradients are in just such a way, and small perturbations around local equilibrium for a fluid with viscosity are proven to a physicist's satisfaction to be unstable. I mean, you know, if you linearize, they will all go away. For hydrodynamics with spin, I'm not so sure.
Okay. Well, let's perhaps some kind of spin orbital coupling that will bring sort of relaxation, right? Generally, you would expect something like that.
Yes, of course. I just wanted to ask. I just wanted to understand. I mean, it was interesting that T-vorticity, this Masoud's previous comment that T-vorticity can be connected to a canonical momentum. This is in Lagrangian hydrodynamics, which assumes local equilibrium somehow or not.
Yeah. Okay. Any more comment? Yeah.
On this.
Hi, Kat.
May I answer this question by Giorgio? Yes, the thing is that actually in the literature, there's no place that you can find that T-vorticity is a conjugate momentum. But in at least in the astrophysical literature, you can find that there is something like a specific enthalpy times times the velocity that becomes the conjugate momentum. But if you write the equation in a way that the fluid is not charged, then you will find that essentially this specific enthalpy is going to be replaced by the temperature in the case of an uncharged fluid. This is not a very and if you got that thing, you can if you assume that the Kelvin theorem holds for some, I don't know, at some approximation, then you can put some initial condition.
For ideal hydrodynamics, Kelvin's theorem holds, of course, and moreover, it's another current. You can see it as a northern current of a non-local symmetry. So whatever.
Yeah. Okay, gentlemen, I think it's getting late for some people on some time zone. So I'm gonna go ahead and stop the recording, and I think we have a very good discussion here. It's a little bit it's over time a lot, but I think it's a very good discussion. So I'm gonna stop the recording. Let's thank the speakers and all the discussion participants again. So thank you very much.
Thank you.